Good day, my name is Mkhulisi, student number 28131192, and I'll be representing group number 37. Welcome to our fluid mechanics experiment on sluice gate flow analysis. In this setup, we explore how water behaves as it passes beneath the sluice gate in an open channel. By applying Bernoulli's principle along with different streamlines, we'll derive the downstream velocity in terms of the upstream and downstream water height, which is capital letter H and small letter h. This experiment helps us understand real-world hydraulic structures and the dynamics of inviscid flow in open channels. Let's dive into the physics behind the flow. Thank you.
Good day, my name is Mecn, student number 28099206. I'm representing the setup and objective. In this experiment, we analyze water flow beneath the sluice gate in an open channel. The upstream water level is capital letter H and the downstream level is small letter h. Our goal is to determine the downstream velocity using Bernoulli's equation, assuming inviscid flow and negligible upstream velocity. Thank you.
Good day, my name is Mecn, student number 2672335. Continuing from my group member statement, Bernoulli's equation relates pressure, velocity, and elevation along a streamline. Since the flow is inviscid and V1 is approximately 0, we can simplify the equation to compare energy levels upstream and downstream of the gate.
Teams, my name is Shalom Marutla, student number 2740702, and I'll be continuing from where my previous colleague has left off. First, we apply the Bernoulli's equation along a streamline at the top of the flow. Upstream, the energy is mostly due to elevation, capital letter H. Downstream, the elevation is small letter h and the velocity is v. We have used the equation that has been given to us to solve our problem.
My name is Khalalazan Lidira. For streamline along the bottom, we apply Bernoulli's equation along the bottom streamline. Here, both upstream and downstream points are at the same elevation, so the energy difference is purely due to velocity. This gives us V is equals to square root of 2g capital H. This assumes that bottom pressure remains hydrostatic.
My name is Mahaura Patelo, student number 2856810. So basically, in conclusion, the downstream velocity depends on which streamline we analyze. These results help engineers design hydraulic structures like spillways, floodgates, and understanding flow behavior is key to managing water resources efficiently. Thank you.
Okay, good day. As I said before, my name is Mecn, and this is Group 37. Now, looking at the selected question, it reads that the velocity downstream of the sluice gate is assumed to be uniform. Express V in terms of H, capital letter H, and small letter h for this inviscid flow. Use a streamline. So the objective is to determine the velocity at A along the top downstream and B along the bottom downstream. A few assumptions need to be made before tackling this question. The flow is inviscid. The velocity downstream of the sluice gate is uniform. The upstream velocity is 0. The flow is incompressible. Bernoulli's equation is applicable as this is a streamline. The pressure at the free surface upstream and downstream is atmospheric. The elevation downstream at the top of the jet is h and at the bottom is 0. Hydrostatic pressure applies upstream at the bottom, so the pressure is equal to rho gh. Now, because of these assumptions and looking at the question placed in front of us, the derivation of the final equation for the velocities at A, the top of the streamline, and B, the bottom of the streamline, can be derived. This is the derivation of said equations, and yes, here we go. At the bottom of the streamline, the velocity is the square root of 2g capital letter H, and at the top of the streamline, the velocity is equals to the square root of 2g capital H minus small letter h. Thank you.
the results discussion. The objectives of this investigation were successfully met, as both theoretical and experimental approaches were used to study flow under a sluice gate. Theoretical analysis using Bernoulli's principle provided an ideal prediction of downstream velocity, while a simple low-cost apparatus allowed for practical measurement of flow parameters such as upstream head, gate opening, and actual velocity. The results showed that theoretical velocity were much higher than the actual measured values for all gate openings due to real fluid effects like viscosity, turbulence, and flow separation, which cause energy losses not accounted for in the ideal model. As the gate opening increased, both theoretical and actual velocity slightly decreased, aligning with the expected trend from Bernoulli's principle. Overall, the experiment clearly demonstrated how real flow deviates from ideal prediction, fulfilling the study's aim of linking theoretical understanding with real-world fluid behavior.